Today in this video, we are going to discuss the differential equations reducible to exact differential equation. That means the equation in the form m dx plus n dy is equal to 0, but del m over del y is not equal to del n over del x. So type 1. If del m over del y minus del n over del x upon n is equal to fx. That is, if the value of this expression is equal to some function of x only. So in this case, the suitable integrating factor is always e raised to the power integral fx dx. Means whatever this function is, we have to substitute this function in this formula e raised to power integral fx dx. This gives us the integrating factor. Let us take an example. So suppose this is the differential equation to be solved. 2x log x minus xy dy plus 2y dx is equal to 0, which may also be written as 2y dx plus 2x log x minus xy dy is equal to 0, which may be compared with m dx plus n dy is equal to 0. So comparing with this, we get m is equal to 2y and n is equal to 2x log x minus xy. So if we find partial derivative of this with respect to y, we get del m over del y is equal to 2. And if we differentiate n partially with respect to x, we get del n over del x is equal to 2x into differential of log x 1 upon x plus differential of 2x is 2 and log x as it is. We have differentiated this term with the help of product rule. Then next, the partial derivative of this term is y, because variable is x only and y is taken as constant. So this is cancelled, and finally we get 2 plus 2 log x minus y. So obviously del m upon del y is not equal to del n upon del x. So now if we form this expression, that is del m over del y minus del n over del x upon n. So let us find it out. Del m over del y was 2 and del n over del x was 2 plus 2 log x minus y. Divided by n. So n is 2x log x minus xy is equal to, opening the bracket, this minus will make all the signs changed. So we get 2 minus 2 log x plus y divided by, from these two terms we may take x common. So x, inside the bracket we get 2 log x minus y. In the numerator, positive 2 is cancelled by negative 2 and only two terms are left, that is minus 2 log x plus y. So if we take minus common out of this term, we get minus 2 log x minus y upon x 2 log x minus y. So we observe these two brackets are identical, can be cancelled. So we are left with only minus 1 upon x. So obviously this is a function of x only. So that is, this condition is satisfied. Del m over del y minus del n over del x upon n is equal to fx. So in this case, Our suitable integrating factor will be e raised to the power integral fx dx. Integrating factor is equal to e raised to the power integral fx dx, and this is our fx. So e raised to the power integral minus 1 upon x dx. So e raised to the power minus 1 upon x, the integral is log x. So e raised to the power, this may be written as log x raised to the power minus 1, and e raised to power log eliminate each other. So we get only x raised to the power minus 1, which may also be written as 1 over x. Given equation, so since integrating factor is 1 upon x, now we need to multiply both sides of this equation by 1 upon x. So 1 upon x into 2x log x minus xy dy plus 1 upon x 2y dx is equal to 0. Now we may take x common out of it, so we get 1 outside because this x will cancel this x and we are left with plus, and here we get 2y upon x dx is equal to 0. We may rearrange it, writing this term first. We get 2y upon x dx plus, writing this after that, 2 log x minus y dy is equal to 0. Let it be equation number 1. If we try to check the exactness of this differential equation, so comparing with the standard format, m dx plus n dy, our m is 2y upon x and n is 2 log x minus y. 2 log x minus y. So now if we differentiate this with respect to y partially, del m over del y is equal to 2 upon x, and if we differentiate it partially with respect to x, so we get 2 upon x and derivative of y is 0. So we get del m over del y and del n over del x both equal to each other, 2 upon x. That means now this equation is exact differential equation. So for that, the solution is integral y constant m dx plus integral terms not containing x dy is equal to c. So m is 2y upon x. So write it down. Integral y as constant 2y upon x dx plus integral terms of n not containing x. So first term contains x, we have to ignore it. Second term doesn't have x, so we have to consider minus y only. So terms of n not containing x is minus y, dy is equal to c. Now, since y is taken as constant in this term, so 2y is constant, take this out, 2y, integral 1 upon x dx, and this minus should be taken out, minus integral y dy is equal to c. Now 2y and integral of 1 upon x is log x, minus integral of y is y square upon 2 is equal to c. So this is the required solution of the given differential equation. Now type second is when del n upon del x minus del m upon del y upon m is a function of y only. That means the value of this expression is equal to some function of y only, then the suitable integrating factor is equal to e raised to the power integral phi y dy. So for better understanding, let us take an example. So the example is solve the differential equation y raised to power 4 plus 2y dx plus xy cube plus 2y raised to power 4 minus 4x dy is equal to 0. So first let us check it whether it is exact differential equation or not. So comparing with m dx plus n dy is equal to 0, we get m is equal to y raised to the power 4 plus 2y and n is equal to x y cube plus 2y raised to the power 4 minus 4x. If we differentiate it partially with respect to y, we get del m upon del y is equal to 4y cube plus 2. And if we differentiate it with respect to x partially, we get del n upon del x is equal to y cube. The derivative of second term is 0 because there is no x in it. So derivative of third term will be 4. So obviously del m upon del y is not equal to del n upon del x. Thus the given differential equation is not an exact differential equation. So now let us check whether this condition is satisfied or not. So this is del n upon del x minus del m upon del y upon m. So we need to find out the value of this expression. So del n upon del x minus del m upon del y upon m is equal to del n upon del x is y cube minus 4 minus del m upon del y is 4y cube plus 2 upon m y raised to the power 4 plus 2y. Simplifying numerator, we get y cube minus 4 minus 4y cube minus 2 upon y raised to the power 4 plus 2y. In the numerator, we get minus 3y cube because there is positive y cube and minus 4y cube. So we get minus 3y cube and minus 4 minus 2 minus 6 upon, here in denominator y is common out of these two terms. So taking y common, we get y cube plus 2. In the numerator, if we observe, minus 3 is common. So taking minus 3 common out of these two terms, we get y cube plus 2 upon y cube plus 2. Obviously, these two brackets are identical, so can be cancelled with each other. And we are left with only minus 3 upon y, which is purely a function of y. So this condition is satisfied. So in that case, the suitable integrating factor is equal to e raised to the power phi y dy. So integrating factor is equal to e raised to the power integral phi y, which is minus 3y dy. That is equal to e raised to the power. Minus 3 should be taken out. Integral 1 upon y dy. So e raised to the power minus 3. Integral of 1 upon y is log y, which may also be written as e raised to the power log y raised to the power minus 3. E raised to the power log is eliminated and we get only y raised to the power minus 3 or 1 upon y cube. So this is our suitable integrating factor. Now proceeding from this step, we have found integrating factor as 1 upon y cube. So now we need to multiply both sides of the given differential equation by this integrating factor. So multiplying both sides of the given differential equation by 1 upon y cube. First term is y raised to power 4 plus 2y dx and we have to multiply it by 1 upon y cube, that is integrating factor. So 1 upon y cube multiplied by y raised to the power 4 plus 2y dx. So now we have to multiply this by 1 upon y cube. So plus 1 upon y cube, that is the integrating factor, and the expression xy cube plus xy cube plus 2y raised to the power 4 minus 4x dy is equal to 0. Now, if we multiply these two terms by 1 upon y cube, the first term becomes y plus second term becomes 2 upon y square dx plus, if we multiply first term of this bracket by 1 upon y cube, we get x only plus second term 2y raised to the power 4 divided by y cube. So we get 2y, and next term is minus 4x upon y cube dy is equal to 0. So this may be written as y plus 2y raised to the power minus 2 dx plus x plus 2y, and this term may be written as 4x y raised to the power minus 3 dy is equal to 0. Now let us check whether it has become exact differential equation or not. So again we have to compare it with the standard form m dx plus n dy is equal to 0. So now m is equal to y plus 2y raised to the power minus 2, and n is equal to x plus 2y minus 4x y raised to the power minus 3. So if we differentiate m partially with respect to y, del m upon del y is equal to 1 minus 4y. Differential of y raised to the power minus 2 will be minus 2 y raised to the power minus 3. So it becomes minus 4y raised to the power minus 3. And if we differentiate this expression partially with respect to x, we get del n upon del x is equal to derivative of first term is 1, derivative of second term partially with respect to x is 0 because there is no x in it, and the derivative of third term partially with respect to x will be minus 4y raised to the power minus 3. So we observe that del m upon del y is exactly equal to del n upon del x. So it implies that del m upon del y is equal to del n upon del x. So this equation has become an exact differential equation. So its solution is integral y taking as constant m dx plus integral terms of n not containing x dy is equal to 0. So integral y is taken as constant, m is y plus 2 y raised to the power minus 2 dx plus integral terms of n not containing x. Now observe n, first term contains x, third term contains x, only middle term doesn't have x, so we have to take only this term. 2y dy is equal to c, sorry, here should be c, not 0. So now integrating these two terms with respect to x, so y is taken as constant, so that the integral of this expression will be x y plus 2x y raised to the power minus 2 plus 2 y square upon 2 is equal to c. This 2 is cancelled by this 2 and we are left with xy plus 2x y raised to the power minus 2 plus y square is equal to c. We may write it as x y plus 2x upon y square, because y raised to the power minus 2 may be written as 1 upon y square plus y square is equal to c. So you may leave your answer here or you may write it as this one. Again, you may also take x common out of these two terms. So taking x common out of this, we get y plus 2 upon y square plus y square is equal to c. Now type 3, where m is equal to y into some function of x and y, and n is equal to x into some function of x and y. Then the integrating factor is taken as 1 upon m into x minus n into y. Now let us take an example. Y bracket xy plus 2x square y square, that is y into some function of x and y dx, plus x xy minus x square y square bracket close dy is equal to 0. So obviously this is in the form m dx plus n dy is equal to 0, where m is this, m is equal to, and n is equal to x bracket xy minus x square y square. So obviously m is equal to y into some function of x and y into fxy, and n is equal to x into some function of xy. So we have to take integrating factor as 1 upon m into x minus n into y. So 1 upon m, that is y x y plus 2x square y square into x minus n, which is x xy minus x square y square into y. Now if you multiply these two, we get x y bracket xy plus 2x square y square, and if we multiply these two, minus x into y xy minus x square y square. So 1 upon, obviously xy is common out of these two terms, so taking xy common, inside the bracket we get xy plus 2x square y square minus xy minus into minus plus x square y square. Now this xy positive, this xy negative are cancelled with each other, and we are left with 1 upon x into y, and these two terms are like 2x square y square plus x square y square becomes 3x square y square. Finally, we get 1 upon, as the given differential equation was this, so y xy plus 2x square y square dx plus x xy minus x square y square dy is equal to 0. So because we have found integrating factor as 1 upon 3x cube y cube, now we have to multiply the whole equation by this integrating factor. So multiplying by 1 upon 3x cube y cube, so we get y xy plus 2x square y square upon 3x cube y cube dx plus x xy minus x square y square upon 3x cube y cube dy is equal to 0. Now simplifying this, if we take xy common out of these two terms, because we have taken xy common out of these two terms, so it becomes x y square because there was y outside. So xy square, inside the bracket we get 1 plus 2xy upon 3x cube y cube as it is dx plus, and here if we take xy common out of these two terms, so it was x outside there, so it becomes x square y inside 1 minus xy, and denominator 3x cube y cube dy is equal to 0. So obviously the 1 power of x is cancelled, 2 powers of y are cancelled, and here 2 powers of x are cancelled, and 1 power of y is cancelled. Now we get 1 plus 2xy upon 3x square y and plus 1 minus xy upon 3xy square dy is equal to 0. So if we split it up, we get 1 upon 3 x raised to the power minus 2 y raised to the power minus 1 plus 2 upon 3 x raised to the power minus 1, simplifying these two, and y will be cancelled by y dx. So simplifying this expression, we get 1 upon 3 x raised to the power minus 1 y raised to the power minus 2 minus y raised to the power minus 1 dy is equal to 0. So now if we compare this with m dx plus n dy is equal to 0, here m is 1 upon 3 x raised to the power minus 2 y raised to the power minus 1 plus 2 upon 3 x raised to the power minus 1, and n is equal to 1 upon 3 x raised to the power minus 1 y raised to the power minus 2 minus y raised to the power minus 1. Now we check del m over del y and del n over del x. So we get, differentiating this partially with respect to y, del m upon del y is equal to minus 1 upon 3 x raised to the power minus 2 y raised to the power minus 2. Differential of this term is 0. And if we differentiate this with partially with respect to x, del n over del x is equal to minus x raised to the power minus 2 y raised to the power minus 2 upon 3. Differential of this term is 0. So we get the same expression on right hand side of both. So it implies that del m upon del y is equal to del n over del x. That is, this becomes exact differential equation. So the solution of this is integral y constant m dx plus integral terms of n not containing x dy is equal to 0. So proceeding from this step, integral m dx when y is taken as constant plus integral terms of n not containing x dy is equal to 0, we have written integral y is constant and m is 1 upon 3 x raised to the power minus 2 y raised to the power minus 1 plus 2 upon 3 x raised to the power minus 1. We have written this dx, m dx, and integral terms of n not containing x. So if we observe n, so first term has x, so we have to ignore it, and the second term doesn't have x, so we have to take this. So this is minus y raised to the power minus 1 dy is equal to c. So now if we split it up, we may write it as 1 upon 3 1 upon x square y, because x is to the power minus 2 y raised to the power minus 1 may be written as 1 upon x square y dx, and then 2 upon 3 and x is to the power minus 1 as 1 upon x dx, and plus into minus minus, and y raised to the power minus 1 is 1 upon y dy is equal to c. So since here we have to consider y constant in the first term, so 1 upon y should be taken out. So 1 upon 3y and 1 upon x square is written as x raised to the power minus 2 dx. 2 upon 3 integral of 1 upon x is log x minus 1 upon y dy, that is log y, is equal to c. So integral of x is to the power minus 2 is x is to the power minus 1 upon minus 1, 1 upon 3y as it is outside, and these two terms as it is equal to c. So this term may be written as minus 1 upon 3xy plus 2 upon 3 log x minus log y is equal to c, and that is the required solution of the differential equation. Now type 4 is if a differential equation is given in the form x raised to the power alpha y raised to the power beta bracket my dx plus nx dy is equal to 0, where m and n are some arbitrary constants. So the suitable integrating factor in that case is equal to x raised to the power km minus 1 minus alpha into y raised to the power kn minus 1 minus beta. Now let us take an example. We have to solve bracket y cube minus 2x square y dx plus 2x y square minus x cube dy is equal to 0. Taking this as m, this as n. So if you check del m over del y and del n over del x, so you will find del m over del y is not equal to del n over del x. So this is not an exact differential equation, but if we open up this bracket, we get y cube dx minus 2x square y dx plus 2xy square dy minus x cube dy is equal to 0. Now if we group these two terms, y cube dx plus 2x y square dy and these two, 2x square y dx minus x cube dy is equal to 0. Out of these two terms, y square is common. Inside the bracket we get y dx plus 2x dy. Out of these two terms, if we take plus x square common, inside the bracket we get minus 2y dx minus x dy is equal to 0. Let it be equation number 1. Now we have to compare these two terms separately with standard form x raised to the power alpha y raised to the power beta m y dx plus nx dy. So if we compare for this, for y square y dx plus 2x dy, we write this expression in the form of this. We may write it as x raised to the power 0 y square 1 into y dx plus 2 into x dy. So if we compare these two expressions, so alpha is equal to 0, beta is equal to 2, m is equal to 1, and n is equal to 2. Now for this term, we have to find integrating factor with the help of these parameters. So integrating factor, as we have given in the beginning, suitable integrating factor is x raised to power km minus 1 minus alpha into y raised to power kn minus 1 minus beta. So now we have to substitute the value of m, n and alpha beta in this. So we get integrating factor is equal to x raised to the power km minus 1 minus alpha, so x raised to the power m is 1, so it becomes k minus 1 minus 0 into y raised to the power kn, n is 2, so 2k minus 1, beta is 2, so minus 2. So ultimately we get x raised to the power k minus 1 and y raised to the power 2k minus 3. Let it be equation number 2. Now we have to consider the second term. So second term, which is x square minus 2y dx minus x dy, may also be written as x square y raised to the power 0 minus 2y dx minus x dy. So comparing with this standard format, we have alpha is equal to 2, beta is equal to 0, m is equal to minus 2, and n is equal to minus 1. So if we substitute these parameters in integrating factor for this expression will be x raised to the power k into m. M is minus 2, so it becomes minus 2k minus 1, and alpha is 2 here, so minus 2 into y raised to the power kn. N is minus 1, so it becomes minus k minus 1 minus beta. Beta is 0, so finally we get x raised to the power minus 2k minus 3, y raised to the power minus k minus 1. Let it be equation number 3. After that, what we have to do, we have to compare the powers of x in these two equations, in these two expressions. That means the integrating factor for the first term and suitable integrating factor for the second term of equation number 1. We have to compare the powers of x. Here power of x is k minus 1, and here in equation number 3 the power of x is minus 2k minus 3. So we write k minus 1 is equal to minus 2k minus 3. Here we should take some other notation because these two must be different. So this is for the second expression, so we should write it k dash. So here dash dash. Yeah. Now if we compare the powers of x, k minus 1 is equal to, here x power of x is minus 2k dash minus 3. So 2k dash minus 3, and if we compare the powers of y, so here power of y is 2k minus 3. That is equal to power of y here in the third equation is minus k dash minus 1. So it implies that from here we get k plus 2k dash is equal to minus 2. And simplifying this, we get 2k plus k dash is equal to plus 2. So now we have to solve these two equations for k and k dash. So multiplying this equation by 2, we get 2k plus 4k dash is equal to minus 4. 2k plus 4k dash is equal to minus 4. And write this equation as it is, 2k plus k dash is equal to 2. Now we have to subtract minus minus minus. 2k negative positive are cancelled. 4k dash positive, 1k dash is negative, so we get 3k dash is equal to minus 4 minus 2 minus 6. So it implies that k dash is equal to minus 2. Substituting this value in either of these two equations, so I am going to substitute in this. So we write k plus 2 into minus 2 is equal to minus 2, or k minus 4 is equal to minus 2 implies that k is equal to 2, because transposing 4 to that side it becomes 4 minus 2. K is equal to 2. Now next step is we have to substitute these two values of k and k dash in either of these two equations, in equation 2 or in equation 3. We get the same expressions on right hand side. So let's substitute in this the value of k, which is 2. So integrating factor is equal to x raised to the power 2 minus 1, that is 1, 2 minus 1, y raised to the power, here 2 2s are 4 minus 3. You get x, y. So you may substitute the value of k in this or the value of k dash in this. You will get the same integrating factor. So in that way we find the suitable integrating factor. Now we have to go back to our given differential equation, that is this differential equation, and we have to multiply this equation by this integrating factor. So first we write the given differential equation as it is, y cube minus 2x square y dx plus 2xy square minus x cube dy is equal to 0. Now we get x y raised to the power 4. If we multiply this by xy, we get minus 2x cube y square dx plus, if we multiply these two terms by xy, we get 2x square y cube minus x raised to the power 4y dy is equal to 0. So now comparing this equation by m dx plus n dy to check it whether it is now exact differential equation or not. So we get m is equal to x y raised to the power 4 minus 2x cube y square, and n is equal to 2x square y cube minus x raised to the power 4y. Now differentiating this with respect to y partially, del m over del y will be 4xy cube, and this term minus 4x cube y. If we differentiate this expression partially with respect to x, we get del n upon del x is equal to 4x y cube minus 4x cube y. So if we observe, del m over del y is 4xy cube minus 4x cube y, and del n over del x is also equal to 4xy cube minus 4x cube y. So it implies that the necessary condition for exact differential equation, that is del m over del y is equal to del n upon del x, is satisfied. So we come to know that this is exact differential equation whose solution will be given as integral y as constant m dx plus integral terms of n not containing x dy is equal to c. So integral y is taken as constant, m is x y raised to the power 4 minus 2x cube y square, x y raised to the power 4 minus 2x cube y square dx plus integral terms of n not containing x, that is in n the first term has x, second term has also x. That means there is no term in n which doesn't have x. So here we take 0, which makes the whole term 0. So that is equal to c. So now integrating this, we take in y as constant with respect to x. We get x square upon 2 y raised to the power 4 minus 2 x raised to the power 4 upon 4 y square is equal to c. So now simplifying this, we get x square y raised to power 4 upon 2, and here this will cancel 2, minus x raised to the power 4 y square upon 2 is equal to c. So this is the required solution of the differential equation, which may also be written as by multiplying both sides by 2, x square y raised to the power 4 minus x raised to the power 4 y square is equal to c dash. That means if any constant term is multiplied by any constant, we have to name it by a new constant, that is c dash. So you may also write it as this, and if you take x square y square common out of these two terms, we get x square y square minus x square is equal to c dash. All these three forms are correct. Whichever you like, you may write as your final answer. So this is how we find the solution of these kinds of differential equations, which are not exact differential equation but can be reduced to exact differential equations.